Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We are just sort of cleaning out our bug list here because we've got some issues that we had set up where we were like, we know we want to go through and sort of fix a couple things that we'd left sitting for a while. And we did a bunch of that, and we're down to the very last few things. We did part of one of them yesterday, which is switching our OpenGL texture downloading from asynchronous to synchronous because drivers were not apparently very happy. And I heard from friends who done a bunch of like porting work to various platforms and stuff too, who were saying, yeah, do not try to do multi-threaded OpenGL, it's a disaster. So I was like, okay, that's totally fair. So we are switching over from multi-thread to single-thread OpenGL texture transfers. And so we did part of the work for that yesterday, and we're going to do the other part of it today. And then hopefully we'll have time to kind of wrap it up and debug it as well, and then we'll have that off our list. And then we can move on to the final item we have, which is Clang compatibility, which is then we'd be done with all of our issue list. Well, all the issue lists that we can do right now. There's someone's like, make sure we have a guy in a tree or stuff like that, which is, kind of a content request. Okay, so the thing that I wanted to talk about today that I thought would be a good time to show how to do this, that's just an educational sort of concept that I thought would be good, that we can use for the system that we were about to implement yesterday, that we set up and we're like, okay, we're gonna, built on. I really just need to make we do a stream where we just go find what that bug is, because it's got to be something we could figure out. And the source code is publicly available for this program, so it seems crazy not to take advantage of that and fix it. All right, so let's see here, day 325, and I want to talk about ticket taking. And ticket taking is pretty cool. It's a multi-threading concept let's try and get that K connected. That's really pretty simple. Once you kind of see how it works, it's really basic, but it's pretty handy. And it's a little bit better than the way that you might do mutexes otherwise. And so I don't think we've done one on Handmade Hero. And inside my codebase at Mali, I think I might literally use them exclusively. Like, I don't even know if I use anything other than ticket taking. There might be, I don't really know, but I think I may be almost entirely ticket taking in our code base. So I don't quote me on that, but it's certainly the bulk of the things are ticket taking. So I thought I'd show how to do them. So what is ticket taking? Why do I care about it? Why are we talking about it right now? Well, as you know, if you've been following the series, when we originally did some of our multi-threading work, as you know, you obviously have this sort of fundamental, sort of core problem, which is that when you have two or more threads in the system working on things that could happen at the same time, you have an inherent consensus problem where there's states of things that you need to be coherent, right? You can't just have two threads randomly writing to the same memory or reading from that memory and expect good results, because you don't know the order in which they'll do things, and you could end up with corrupted data. And we sort of did, or not even, I shouldn't say corrupted data, but invalid states, basically, right? And we talked about this a bunch, so I'd encourage you to go maybe listen to the earlier ones if that sounds very strange to you or you're not sure what I'm talking about. But in general, just to recap, we could take a very, very simple concept such as a linked list that we've done many times, singly linked list that we've done many, many times on Handmade Hero. And if you think about the operations that are involved, right, if we think about a linked list, let's say that I just make the very simplest kind that I possibly could. And so I've got a link struct, and inside that link struct, I just have a pointer to the next thing, right? And then it doesn't even matter what the data is in it. We don't care. We just know there's some data in it and a next pointer. And so all we have, the very simplest thing that we could possibly have, we just have a first pointer, right? And that's all there is to it, right? Now you've seen me write the code for adding and removing things from a linked list many, 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 many times. And so you kind of know exactly what the code for this type of structure looks like when we need to maintain it, right? If we want to add, so here's like where we would add a link, right? The add code is extremely straightforward, right? I'm going to get, whatever my link is, my new link here is just going to be equal to, something, whatever it is. I allocate a new one, or I grab one off a free store, or who knows, doesn't matter for the present thing. So I have a new one, right? And I'm going to say that whatever the existing first thing is going to become my next pointer, right? And then the first thing is going to be me. Okay, and so if you think about what that happens diagrammatically, right, is previously I just had this first pointer, and it's pointing to something. We don't know what. It could be null, right? It could be nothing, but it possibly is an existing linked list with some number of chains in it, right? And so then I come along and I've got this new one that I've made, and so what I want to do first is make it point to this one, whatever's there, and then make first point to it. Right? And I have to do them in that order because if I did them in the other order, I would lose this one, right? Because I'm using the value of first here, so I can't overwrite it prior, right? So it has to be exactly this, right, in order to do it. If that makes sense. Now I'll mention something else. There is another way you could think about this, which is if you want to be Sly Mr. Sly Pants, you can initialize new next, like whatever the whatever this value is, new next equal to new. Like I could be Sly, right? I could do new arrow next equals new, like points to itself, and then do swap first and new next, right? Because then it's like first goes into here and new next goes into there. So it's worth noting that actually if your CPU had sort of an atomic swap operation, you can almost make, well not almost, you can make this operation be entirely atomic because all you have to do to add something to the beginning of a linked list is an atomic swap and you can do it. Just pointing that out. Not so easy is to delete something from the list, right? To remove something from the list. And I guess maybe I'll call it remove because it's not really delete, I suppose. So if I'm going to remove something from the list, now what I've got to do is say, all right, the first pointer, whatever that is the link that I'm going to get, right? So I've got an old link that comes off here, right? And then what I want to do is I want to set first equal to whatever old next was, right? But I can't just do that because if I just did that, I could possibly crash because I don't know that there's anything on the list ahead of time. So technically I have to do an if here, right? I have to say if I actually got an old thing, then I can do it. Now you'll notice there's a distinct difference between these two things. And let me write that out a little clearer. That was not great. I probably should have put the left space for the if. But I have to say if old, right? Then we can do first equals old first. I'm sorry, next. But right, we know that I can't sort of access that guy until I've actually verified that he exists. So there's a distinct difference between these two. This one is like essentially conditional free, right? This is just moving some memory around in a very predictable way, either by doing two writes like so, or a swap, right? Depending on how you want to structure it. This one, on the other hand, has to do a read, a test, and then a write. That's just the way it is. Okay, so now the question is, what if we want these things to be happening for more than one thread at the same time, right? What happens if I want to start having this stuff be multi-threaded, so people are adding and removing things from one of these singly linked lists, let's say, without regard for the fact that other people may be using the list at the same time. And I want to guarantee that I always have a real linked list and I don't end up losing a link somewhere or getting into some situation where somebody's pointer points in the middle of nowhere or who knows what happens, right? I want to maintain the integrity of the list. Well, you can immediately see the problem with multi-threading these. If you just leave the code for add the same as it was, then the problem is it's a two-step process, right? Now, like I said before, if you happen to have an atomic swap, right, where I can actually swap two memory, and I don't mean swap a register in a memory location, right? I mean swap two memory locations atomically. If you happen to have something like that, then you could do this in one atomic operation, and add can be completely mutexless. It can just go. But if you don't have that, you have two steps, and if you have two steps, then you have the problem of somebody can intercede, and once you have done this one step here, they may come do their odd operation while your thread may have gotten swapped out or something, or who knows what, or is busy like waiting for some piece of memory. And now when you do first equals new, you've corrupted the list because they added something at the beginning of the list. Then you overwrite that the correct first pointer with your first pointer, orphaning whatever they put in there, right? You've essentially, their add will essentially disappear because you prepared your new link pointing to the head, the previous head of the list. They came and added a new head, and now you overwrote the head pointer to your pointer. So you've totally, their addition has just disappeared, right? Now, same thing's true of removed. When I pull this off and then start to test it, well, somebody in here could have done another remove, and now we're both removing the same element, right? Or they could come in and remove 2 or 3 elements, and then I write this back in there, and that's wrong because it's right. So anytime you have a couple steps in the instruction, you're at a point where you have two choices. You certainly can't leave the code as it is, so you can either do one of two things. One is you can try to create an algorithm that's just about doing atomic move or compare operations that will work, right? And that's for if you want to be Mr. Fancy Pants, and I don't really necessarily recommend doing a whole lot of that. And the other is you can do a fast mutex, right? You can do something that's very low cost, but that basically ensures that only one person does things at a particular time, right? And so that's what I prefer to do, is to have a very, very fast mutex. A mutex that only takes a few instructions in the case where it's uncontended, and only 100 instructions or something, 200 instructions, whatever, if it is contended. So very, very lightweight, and you can use them everywhere, and they don't really slow your code down, right? That's what I want. I don't want some big, heavyweight, nasty mutex thing that has state or any of these other things. No good, right? Well, state that has operating system state or anything like that. So I want something very, very, very simple. My threads are not going to go to sleep or anything like that. They're just going to do quick checks and then lock up for a couple cycles if somebody else is in it, and then proceed, that sort of stuff, right? So ticket taking is a way that we can implement a really good, fast, simple mutex for little chunks of code that we just want to wrap, so that we know that when we're going to access this particular piece of data, we just want to make sure that we're the only person who does this simple atomic operation on it, and then we can proceed, right? So what is ticket taking about? Well, we know we have this concept of atomic operations in the CPU, and we talked about these, and we talked about the MESI protocol, right, which is the thing inside the CPU cache, which allows different CPU cores and different entirely different physical processors on a multi-processor machine, not just a multi-core machine, to get the state of memory straight between themselves, right? And we know that we have certain operations we can rely on that will go through that MESI protocol to do the right thing and make sure that we can do stuff like test and set a particular value in one operation without the possibility of another core or processor coming in there and doing something in between, right? And one of the things that's really great, and Fabian pointed this out to me, actually it was in the middle of Handmade Hero before he pointed out to me, I think I mentioned it, there's a really great paper, and I'll mention it again, it's called Weight-Free Synchronization. that's by this fellow right here, Maurice Herlihy. And this is probably one of the best papers that there's been in like the history of papers, and certainly in the history of multi-threading. I don't think you could get a better paper than this. It's insanely good. And the important part of this paper, the takeaway, if you take away nothing else, it's that atomic compare exchange is the fundamental building block for all consensus algorithms. And the reason for that is that Maurice Herlihy basically proved in that paper that for the vast majority of things you might want to try to do concurrently, it is literally impossible to do them without that operation. Like, that is the fundamental operation. Atomic increment is not a fundamental operation, nor is decrement, nor is swap. It's only atomic compare exchange that actually lets you build everything. And so at some level, you can kind of think of it as like, well, the best you're going to be able to do is certain very specific other sorts of things with the other atomic operations. But for anything real, atomic compare exchange is where it's at, right? But anyway, details for the paper, you can go ahead and read them. It talks about consensus numbers and all sort of the fundamental things. And Maurice Herlihy invented all that, as far as I can tell. Like, that paper is the paper where he invented it all. He's like, hey guys, guess what? I figured it all out. We can stop now. And that was it. So with our atomic operations, the one I'm going to focus on here is atomic compare exchange. And basically the one that there's various flavors that these sorts of things could take, but what I want to talk about is specifically the atomic operation. That, again, we've done it before on Handmade Hero, but it's essentially an atomic operation that says, if, like I've got some pointer, right? So if my target here, I guess I'll call it the destination. If the destination equals an expected value, right, set the destination equal to a new value, right? And in either case, I want you to return to me what the old value was, right? And even that I don't really necessarily need. All I really need to know, right, is, what was I going to say? I don't even remember what I was going to say. Oh, all I really need to know is whether the assignment succeeded, right? So that is a pretty big one, right? And the other one that I wanted to mention is the super simple one that we've also done on Handmade Hero, which is just atomic increment, right? An atomic increment is just one that says, all right, I just need you to add 1 to the value of whatever is in this location. I don't care what the value was beforehand. I just need you to add something to it, but I need you to tell me what it was before, right? And so that one's really simple. That one's basically just like, return star dest plus plus, or depending on the situation, plus plus star dest, right? Kind of a thing. Whether or not it returns you the pre or post incremented value can differ depending on, the processor's implementation or the library that you're using. The compiler that you're using to access that could choose to do it different ways and so on as well, right? So just keeping these in mind, these are the atomic building blocks that we tend to work with. And I think that's pretty much everything I wanted to say to motivate this whole thing. Yeah. All right. So let's talk about our ticket-taking scenario now. So ticket-taking is a very, very, very simple thing we can do. And it actually doesn't really involve well, I guess you'll see. It doesn't have to involve sort of the more strenuous consensus number thing. So if you look at that Maurice Herlihy paper, I'll kind of make a brief mention back to it in case you want to go read it. But we'll go a little bit forwards from there regardless. So anyway, ticket taking, let's first talk about what we need to have happen, right? So let's say that we have our list, add function here that we were going to do, right? The one that I talked about beforehand, right? And we know that this thing is not atomic. we know that it's not thread safe. So when we call list add, we know that we're going to have to do something to make sure that anyone who's working with this list has prevented everyone else from doing anything at that time, right? So that's just, that's what we're trying to do here. And so we want to basically put something around it. Like we said, we usually call these things mutexes, the phrase mutual exclusion, right? We often call it something a mutex to say, hey, we want to be mutually exclusive when we access this thing. We don't want anyone else to be accessed at the same time because we know the operation we're doing on it fundamentally can't happen at the same time as someone else who might be using it, right? So if effectively what we want to write is something like, begin, access or whatever, end access. And we kind of want to wrap this thing in just a little kind of wrapper that says we're going to begin access here, we're going to end access here, and everything inside here is going to have to happen in a way that is ensured that nobody else can be doing anything to the list at the time when that happens, right? So what we need from this, begin access and end access, what we need is some way of saying, make sure my thread can do what it's going to do. So wait until my thread can do what it's going to do. Also, once I am ready to do what I'm going to do, make sure no other thread can think it can do it. And then when I get down to end access, it's make sure I can tell any other thread, now you can do it, right? So we need a sort of wait till I can do something, lock everyone else out, do the thing, and then unlock so everyone else can come back in. And that's the fundamental mutex operation, right? Okay. So what's one way we could implement this? Just a very, very basic way to implement this, right? Well, if I have my atomic increment, and for purposes of of simplicity here, I'm going to call this atomic add because that way we can think of it as one thing. Like if I want to be able to do +1 or -1, I can, which is kind of handy for talking about this in the general case. I don't actually need it for the ticket taking. Necessarily, but yeah. For describing other ways we might do something, I might. So let's say we could talk about the more general atomic add, not just increment. Although I don't think I'm actually going to need it for the ticket taking, that's a separate issue. So when you look at something like this, how might we do something? Well, you could imagine we could do something where we said, well, all right, let's suppose we have some volatile global int, right? And remember, I'm just going to say again what volatile means. And for the love of God, people, do not write in and send me any of those awful volatile articles that people sent in that were just all wrong. Trust me when I say what volatile means. I'm not lying to you. Volatile just means the compiler cannot assume that it knows what the value is because it read it before. And it is important to use in multi-threaded coding. It is not superfluous, despite what you may have read on really bad Stack Overflow posts. So anyway, let's suppose we have a thing here, a volatile int called mutex, and we have that as a global variable, right? Well, you could imagine we could do something where we could say, all right, let's go ahead and do some sort of a operation on that integer, right? Where we could say, yeah, if we were to, if atomic, add on my mutex with 1, right? Something like, well, you know what? I might do, now I think about this to be safer. Pretend I didn't say this. Let's just use this one because it's much nicer. So let's say I do atomic exchange, right? Compare exchange. There we go. Of my mutex. And I want to do an atomic compare exchange. I want to compare it to 0, and I want to set it to 1, right? And so if I do that and I get back 0, which is what I'm expecting it to be, right? Then I'm going to do my operation. So I'm going to do this. this thing here. If I don't, then I know that this mutex was not set to 0, right? And so what I can do is I can say, well, all right, let's just assume that I do this in a loop forever. And if I ever get to do my operation, I break. Okay? So when I'm going to break, obviously, I need to clear back my mutex so I can add a bit of code in here. Let me clear this out a little bit just to make that a little cleaner. To read, list, add, mutex equals 0, break. And let's assume that this is being done in a for loop, right? So now take a look at what this is going to do. By default, this mutex is equal to 0. I come in here, I say, all right, atomic compare exchange, 0, 1. It's obviously equal to 0, so I stick a 1 in there. I then do my list add. I then clear the mutex back to 0, and I break, right? Off we go. Now, since this isn't an atomic write, just to be safe, you probably want a write barrier in here, right? You want to finish anything that was going to happen. You want a write barrier in here. So in between these two, I probably want a write barrier because as soon as I set this to 0, that means any other thread could start executing, right? To start doing code to it. So you probably want a write barrier in there, but that's a little bit not part of what we actually care about at this particular point. So ignore that temporarily. All right. So now if another thread, while we were in here, came through and did if atomic compare exchange, right? What's it going to do? Well, that mutex is set to 1, right? So this will fail. And so when it fails, right, because it will return a 1, it won't equal 0. When it fails, it'll just skip this and loop and try again. So what will happen is the first thread in will set it to 1 and do the operation. The rest of the threads will just sit there trying to atomic compare exchange over and over and over again until they can. Now, as long as list add is only a few cycles long, which it was like, what, 8 cycles, something? I don't even know. Like, hardly anything. It's just memory time, however long it took to read those things from memory. So maybe it could be up to 300 cycles or something if you had to read the memory. You're only going to block for a very little bit of time if you ever block at all. But chances are you won't block at all because you're probably never going to hit at the same time or very rarely. So most of the time, it's free, right? It's just the cost of this one operation. And that would be an effective mutex, right? We could just do that, and that would implement our linked list. No problem, right? But there is kind of an annoying aspect to implementing the mutex this way, even though we could, and even though we know that atomic compare exchange is a nice, safe, easy way to do this, and nice and clean, and it's good, and you could write your whole program with nothing but atomic compare exchange and it'd be fine, right? This would all be great, and whatever. But there is one downside, and the downside is there's no guarantee that any particular thread who comes into this process will actually get a turn, really, right? Because unless the hardware itself happens to enforce some kind of specific attempt-based something, there's nothing to say who gets to go when. If thread 1 comes through here, or let's say thread A comes through here, right? And A takes that mutex. So A gets into this routine. Now B comes and hits this atomic compare exchange. It fails, right? So it goes into the loop and it's just in a fail loop, right? When A comes out of the mutex, thread C might be coming in at just that time, and thread C could take the mutex, right? And B, even though it was there way before C, is still going to fail and keep on looping. And now thread D comes in and takes the mutex. And A comes in again and takes the mutex. And B just keeps getting unlucky and never happens to be executing at the right time, to actually get the mutex, right? So you can kind of see how if this were an expensive operation, where people actually probably are going to have to wait sometimes, we start to get into a kind of a negative potential situation here, which is that we really don't know that we're being even remotely fair to the people who are trying to take these mutexes. And even though this isn't a hard real-time scenario that we're in, it kind of starts to feel a little bit bad, right? It's like, well, how long has B been waiting at this point? And D could probably stand to wait a little bit, so it really would be better if we let B do its operation. That's, that's going to let the system flow more smoothly if we tend to process people in the order they came in. Hopefully that makes some sense, right? So now let's talk about ticket taking. It's a way to solve exactly the same problem, but in a way that ensures that the people who came in order get retired in order, right? So basically, same exact process as the mutex, but people who come in the order A, B, C, D, E, F, G get retired in the order A, B, C, F, G, which just tends to be a smarter way to make your systems flow. It reduces the possibility of bad churn that can cause things to be highly latent, and in games we tend to not want things to be highly latent that way, right? So a ticket-taking system works by just adding just one more piece of state. That's it. So now I have a volatile int, ticket served, and a volatile int ticket finished, right? And the way that these work is every time someone goes to try and take the mutex, they are going to, instead of spin locking on a value that's like either 0 or 1 based on whether anyone's in there, they're instead just going to first just take a ticket, like you would at a deli counter where they've got one of those little machines where you pull the number out of, right? It's like, what number are you? Oh, you're 83, right? Well, that ticket being system is exactly this thing right here, and this is the now serving, right? That now serving thing, or whatever you want to be. Well, it's not really, but you get the idea. Okay, so how does this work? Well, when I go to actually take the mutex, right, when I want to start doing my operation, I first just do, what's my ticket number? Well, my ticket number is my atomic increment on ticket served. Right? So the first thing I do is I take a ticket. I just increment that ticket served, and now I know I've got a unique number. Because everyone who comes through here is going to do an atomic increment, so no two people will have the same ticket number, and the ticket numbers will be in the order in which the threads hit this line, right? Or I should say the order in which the threads were able to execute this line. So it's up to the Mezi protocol to be fair at that point, but we've pushed it down to the Mezi protocol level, who is deciding what order our threads go in at least, right? We have not introduced any additional churn. So we take a ticket, and now all we have to do is wait while our ticket is not equal to ticket finished. And now technically, we don't want to wait exactly on ticket finished because we have a startup concern here. This is the semantic, this is the idea. But if you think about what happens, this starts at 0, this starts at 0. So when we do the atomic increment, well, we could. As long as the atomic increment returns the previous value, right? So it will return 0 for the first ticket, we're fine, right? So then we just do our while loop. We say, let's wait until ticket finished is equal to the ticket that we had, right? Then I do my operation. So whatever my ops go here, ops go here. And then I do one more atomic increment on ticket finished. Right? But that's it. Barely more complicated than the other code, right? Barely more complicated than the other code, right? It's got 2 atomic operations instead of 1, but those atomic operations are technically even simpler. They're just increment. There's no compare exchange, right? So there we go. Hopefully that makes some sense. So basically all this does is it just says, all right, let's just give out a number to every thread who comes in here, and then we'll have every thread wait until its number is the number that's currently supposed to happen. Very, very simple, right? Really clean. You just debug it once, and then you can use it everywhere, and it's pretty great, right? And it has this really nice property, unlike other kinds of mutexes you might do, where instead of it randomly letting threads go depending on some who knows what, it's always based on pretty much first in, first out, which is just a better way to go. All right, so hopefully that all made some sense, and like I said, hopefully that's enough of a brush up on the multi-threading stuff that what I'm about to do is not going to seem silly and weird. But let's try and get that implemented now in the code base. So I'm going to go ahead and open up Handmade code, and I'm going to go ahead and say that we've got in our Handmade shared here. Where's my platform? I believe we have our add, or our, we've got our atomic. There we go. So we've got our atomic add U64 here, and we don't really need a U64. But I guess since that's what we've got, we can use it. Might as well, right? So that's what we'll do. So let's say I want to make one of these things. I'm going to do exactly what I just said, like literally exactly what I just said. So here's a struct. I'm going to call this a ticket mutex. And what I want to do here is I want to have a U64, right, a volatile. I guess I've been putting them after. Ticket and a U64. I guess we'll call this serving, right? And that's all I need to implement the ticket mutex. I just need these two here. Now, one thing that I've never been 100% sure about, because I've never actually done the timing, is I always wonder whether these should be padded so that they're on separate cache lines. Does that make sense? Because since the Mezi protocol will do sharing based on the cache lines, I always wonder if it's better to have your tickets and your serves on separate cache lines. It'd be a really hard thing to measure, and you'd need some code that was really hitting these mutexes hard. So I don't actually know, I've never tried to actually construct a thing to test it, but I've always just kind of wondered. I don't know if anyone's ever really done that. Maybe they have, and someone could send me a link. But anyway, ignoring that. So now we've got two things, right? We've got one which is like, begin ticket, mutex. And we got another one which is end ticket mutex, right? And these are just going to do exactly what I said. We've got a ticket mutex pointer that we want to use. And what we have to do here is we have to figure out what our ticket is, right? So this is our, our number, right? And we can say, I guess this is probably better called mutex since we have a thing inside it called ticket. Mutex ticket. So maybe that looks better to me. So we can say, I've got to get a ticket out of here, so I know that I have this atomic add U64, right? And hey, that returns the original value prior to adding. That's what we wanted. And the thing that we want to add is just 1. So we could have used increment. There isn't an increment in here already, so we don't have to care. We'll just use that. So this will add and give us back our actual ticket, move it to the next ticket number. We can then just say, why don't you just loop while our ticket number is not equal to the serving number. Off we go. And that's it. That's the entirety of the beginning of the ticket mutex, right? When we want to end the mutex, we don't really have anything else we have to do, right? Because we don't even need to know what our ticket was, right? Because we know that these things are fully locked. So all we have to do then is just say, hey, whatever the serving was, oops, I've got an ampersand up there. Go. Whatever the serving number was, I just want to go ahead and move that forward, right? And that's it. So at that point, we then have a ticket mutex that we can use anywhere that we want to in order to ensure that people who access a particular primitive of some kind will not do so concurrently. So that any threads that happen to be pounding on it, they'll always sort of go in order and serialize just at that one point, right? So that's pretty great. Now, in order to debug that, we actually have to use it, obviously. And so let's go ahead and do that. If we come to our asset processor here, I believe we had a place where we were talking about this, right? we had this add op thing going on here where we had a texture op that we wanted to add. And so what we wanted to do here is exactly sort of what I wrote. We have to have a like a texture op mutex somewhere. So we have to pass that texture op mutex in here. And then we'll have to do our end ticket mutex with our texture op mutex, right? But then when we're in here, we can do whatever we want. And again, although we want to generally keep the amount of stuff we do inside a mutex to be relatively small, since we have done an actual mutex, we can do any code that we wanted here. So it doesn't matter how intricate it is. We don't have to be smart about it or try to figure out how to do a lock-free list where we're just doing things with moves. Because if you look at how simple it is to do the mutex version, and if you can just keep the amount of code in there to be relatively succinct, you're almost always going to be faster than doing some crazy amount of weird atomic operations to try and be lock-free or whatever you want to talk about there, right? So typically speaking, this is a pretty good way to go, especially because it's a lot less error-prone as well, right? So anyway, if we're going to do this operation here, what we need to know is where that's actually going to get stored. And so we need some notion of a place where, when we're doing our loads, where those things can sort of be placed, right? Because this is sort of has to access a global, it's a separate thread, right? It has to be able to access some kind of a global list or something of this nature that can be pulled from and operated on and other things like this. So I don't know exactly how we should do that. I'm not 100% sure, but do we? It looks like we. I don't really know how we want to manage this. I think we do have a place where we get globals of this nature inside handmade.cpp. Let me just double check. I thought there was one here somewhere. Yeah, we have like debug global memory and those sorts of things, right? And so the way that these work is when we first come into game update and render, right? There's this notion of one of these things that gets sort of set. And we're going to need something like this because these are separate threads that are doing this. Well, you know what? I guess we don't even need to necessarily because these separate threads do have data that flow with them. So I suppose we could just target something with them. And that would probably just work. So maybe we'll try to do it that way. Yeah, okay. Maybe I'll try to do it that way. But we will, at the very least, need something stable. Like, it has to be something that sits around. It can't be something that gets re-updated lots of times or anything like that. So we do need something that's going to kind of have a return, a sort of like a flowback kind of a feel to it. It has to be persistent. It can't be per frame, I guess is what I'm saying. Because these threads that are going to access it operate across frame boundaries. So it can't be something specific like that. All right, so if we're going to do something like this, we have game render commands, right? And we also have, I guess, game memory gets passed in. And so what we could do is inside one of these things, like maybe game memory is the best place for it, probably. Let me take a look. Game memory, here it is. Inside game memory, we can probably have a thing in here where we point to whatever that list is, right? So we'd probably have something like, well, platform texture op queue, something like that. I'm just guessing. And so platform work queue is not really defined, and this is something that I would want to define, so I'm going to probably put it here. And what that would have is just that texture op first. Maybe we want texture op last as well. And then we want a texture op first free. And I don't know why I felt compelled to type that so many times. So we've got a first, a last, and a first free. And I think that's probably all we would need, right? And so this guy needs to have the pointer to that. It needs to know where that's going to be. And so when it does the begin and end mutex inside here, it now needs to be able to do the operation that it was trying to do, right? And that operation, I guess texture ops, I think they've got a next on them. I'm pretty sure they do anyway. I could be wrong about that. But what we would need to do here is, I guess, trying to think about how this guy would actually handle the situation where he had to wait. It would be nice if he could, but I don't actually know. I don't actually know how he would go about waiting. This part's going to be a little tricky. And here's why. So when we do texture op ads, the problem that I was thinking of is, I guess we don't really know how many we need, right? That would be the main problem, I would think, here. And to be honest, I guess I don't really know that we need to chain these because we're going to process them all per frame anyway. So it's entirely possible that we wouldn't really ever have to do them in any particular way. But anyway, that's neither here nor there. The point is, the managing the amount of them we have is a little bit, it's unclear exactly how we do that, right? It's possible we could just say, well, we only allow this many per frame to be added, and we just make sure we allocate more than enough for that to have happen. But I'm just not sure what happens in the case where we find that there is an overflow, should there be an overflow. Now, maybe we just say there never can be an overflow, it's just a hard error and everything goes haywire in that case. But, you know, it would maybe be nice to have a better idea of what we could do there. But I'm just not sure, right? I'm just not sure what the right solution is. So I'll have to think about that some more. But, you know, barring that, right, if we are to say just like, okay, there's got to be something on the free list. That's just a requirement, and the game doesn't work if you run out of memory, if you run out of queues here, right? If we say that, and I guess I could put the to-do here, can we devise a soft failure case for running out of ops? What we do want to do is say, all right, well, when we add an op here, we've got the first free, so we'll say, okay, we'll take whatever's on the first free. This is the op we're adding. I guess we'll do it this way. Maybe. So this is the op that we're going to add, our desktop. I guess this can also be a pointer here. This is the destination op. And so what we want to do is essentially do like, you know, something like this where we copy it on. But first, obviously, we have to advance the free list like so. So that pulls us off. This copies our settings on. And then what we have to do is we have to push it onto the list. So then we've got our queue last, do like if queue last, you know, queue last equals queue last. Next equals dest. We'll ensure that dest equals next equals 0, although I guess anyone passing to us probably has already done that. In fact, we could just do this. And if there isn't a last pointer, then it's just queue first equals queue last equals dest. So that basically just allows us to put those ops on there, and it puts them on there inside the mutex so that we know that nobody else can do that, right? And that's really mostly it, I guess. So inside this queue, we then need our mutex, right? Because our queue always has to be able to, like anyone using the queue has to be able to do that. And I guess I don't know where shared gets included here. Does shared not get included here? Yeah. All right. So yeah, we need the ticket mutex to be visible to that code. So you know, we kind of need this guy to be up above, right? We need these guys to be in a nice place. Maybe somewhere up here, for example. There we go. And yeah, so at that point, really, we're mostly down to just routing. We have our add-op calls, and the add-op calls will have to know where to get that texture op-queue. So where's our work happening? Load asset work. There it is. So our load asset work has to have a pointer to this, right? It's got to be something that it can access. And it looks like it's got, doesn't really have anything else there that it could do. Task with memory, I suppose, is one. And, you know, another thing that we could do, like, I'm just going to point this out. It's not something that we should probably do here because it wouldn't really make much sense based on the frequency of things, but I'm going to mention it. Let's suppose we did a ton of adds to this linked list. Just a ton, right? Like thousands per frame. Then we would be hammering on these mutexes a ton, and that would be bad. What we could do instead is inside the task with memory where we have one per thread, we could just build separate lists, one per thread. And when the task gets retired, take them off then and put them onto the main list as a chunk. So that you only take the mutex once, do 2 writes, and you're done, right? And so you can see how, like, how you would choose to structure this would depend a lot on how often you were expecting to do certain operations. Anyway, so yeah, in this case, we need a texture op-queue here. What did I call that thing? Platform texture op-queue. Yeah, that's an address there. And this guy needs to know this. So I believe inside game assets, we need to know where the texture op-queue is. So let's see, inside game assets, that would have to be known. So in here, we've got platform texture op-queue. And so every time we're going to do one of these, we would have to know, what's it called? Assets, just? Yeah. So we just have assets texture op-queue, and off you go. Now, when we actually queue the work, obviously is another time that we're going to have to asset bitmap. Okay, so that's the only time. So in here, when we do our final state loaded, we would have to do a thing that's like, hey, the texture op-queue, it's going to be in here. All right. So last step of the plumbing, might as well do it because we're almost done, even though we're close out of time. So when we pass the allocate game assets thing, let's just pass the texture op-queue there. Platform texture op-queue. And we'll just put it in here. So presumably this is something that will get passed. I think I said we would put it inside game memory. Right. And so when we allocate those game assets, we can just do game memory So now all the plumbing is worked out, and that's all great. But inside our Win32 Handmade, we would have to actually point it at something, which currently we don't. I don't remember how we did game memory exactly, but it looks like game memory is actually static. And since game memory is actually a static thing that doesn't get reallocated, I think we could also probably, if we want to, I think if we want to, we could actually make it just be included, right? I think you could actually just do that. And now I think we would work just fine if it wasn't for the fact that when we actually go to run this, right, there's not going to be anything in the free list, right? Free list is empty. So it should immediately, assert on the free list. So just because, you know, we're in the middle of it, if we were going to populate that free list, let's just say that we went ahead and populated it with a bunch of memory here. If I went and said, you know, give me a virtual alloc of some kind here, you know, something like this, and I said, like, okay, yeah, you know, we've got one of these texture op guys. And maybe we say, like, how many of those do we want? I don't know, texture op count. We've got 1024. That's so many more than we could ever possibly use, right? But whatever. So we allocate an array of 1024 of these. Right? And we get that memory. We then just loop through these. And we say whichever one we're on, excuse me. Whichever one we're on, we just want to set its next pointer equal to whatever the next one is. Oops. So they're all just chained to each other, right? The last guy, we know would want to not set that, so we just don't touch him. And then our game memory texture op queue, all we need to do is set that first free equal to the first guy, right? If we were being Mr. Snarky Pants Snark Bottoms on this particular case, we could even do this because, I mean, why not? Oops. There we go. I mean, you only live once, right? And that would initialize our free list with a giant set of these guys. Yeah. All right. So that's the texture op list. And at that point, I think we've actually implemented everything except the fact that nobody actually ever does anything with the texture op list, right? Which is not exactly the best thing in the world, to say the least. So if we wanted to, we could then actually call our OpenGL manage textures thing and actually have it download the textures and then be done. However, we also do want to be conscientious here and return the last one probably. So I'd probably say something like texture op star last equals 0. And in here, just say like last equals op, sort of a thing. Something like that. And so the reason I want to do that, of course, I'll show you in a second. It's relatively straightforward when you see it. So if I now want to go ahead and do my manage textures, I can do that. In Win32 Handmade, we come down to the place where that would probably happen. So right before we're going to do like our OpenGL stuff or something after that's been filled up. And maybe, maybe we do it right after we get out too. Maybe that's a good time to do it. So we do like our debug frame end thing, and we do our right before we're gonna unload the game code or whatever. Maybe I'm not sure where the best place to do it is. I don't know. Maybe like right here. We'll just do it right here. So right here, when we're about to do our OpenGL managed textures, obviously I sort of said before, we have to be able to make sure that we're always mutexing these things. So I have to take my mutex again, just like I did before. And at this point, I guess maybe the only live onceness of it, I guess I shouldn't have been so YOLO, because I don't really want to type that again. That's just a lot to type. So I suppose I should have actually been more reserved and said, yeah, you know what, texture op. Q maybe is a thing. There we go. Do it that way. You almost only live once. Okay. So then we've just got texture opq, or sorry, platform texture opq. Texture opq equals game memory texture opq. Okay. So our texture opq mutex has to get taken. And released so that we can actually do this operation, because again, this is going to turn through that list. You can't have people sticking stuff on the list in the middle of that. We should take that back. We actually could if we wanted to, and we would have to know not to mess with the stuff that's at the beginning of the list, if that makes sense. But I'm not even going to do that anyway. What I'm going to do is I'm going to put this sort of one down from it and show you what I'm going to do here. I'm going to take the mutex, right? I'm going to say, okay, whatever the first thing is, I'm going to take that first texture op off, and then I'm going to pretend the list doesn't have anything in it anymore. Bam, right? So I'm just going to take the mutex, get in, pull the whole list off, essentially, zero it out, and now I'm holding the whole list, and then untake the mutex. Now everyone can keep adding back in there, so we don't have to, they don't have to wait while I actually go talk to OpenGL, because I just pulled the whole list off and off we go, right? So that's fine. No need to be fancier than that, right? So then I can do last texture op equals manage textures, pass that first texture op. That's going to run through. It's going to return me the last one. So then all I have to do is just put all these guys back on the free list, right? And to do that, that's pretty trivial, right? I just take the mutex again. Remember, everything we do in here has to be mutex. And like I said, I could do that in there if we wanted to, but taking the mutex is so cheap, I just feel like might as well get out of the way, and just in case they want to come in there, might do it. If you really cared, you could test the timing, see if it mattered. I doubt it would either way, but what are you gonna do? So anyway, then I just want to put these guys on the free list, right? I want to make sure they can go on the free list. So then what I do is I say, well, all right, whatever my last texture op was, if I had a last texture op. If I didn't, then you know what, I could even do this. If I don't have any texture ops, then I don't need to put anything on the free list, obviously. So really, it can look like this, I suppose. Right? But assuming I got something, right? So assuming I got something, I have the textures managed, I begin the ticket mutex, and then I say, okay, whatever was on the first free list before, that's going to be whatever my last texture op I found was. I'm going to point him at that part of the first free list, and then I'm going to set the first free list to point to me, right? And I think that should do it, but I've written a lot of code there without really doing much, so probably won't work. But that's the basic idea. And now we can go to the Q&A. We might as well run it to see where we foul up horribly. Oh, hey, look, it almost worked, which is pretty hilarious. So we still have some debugging to do. I'm kind of surprised that worked at all the first time, but that's fine. So we can go to the Q&A now, and then tomorrow we'll finish that up, the debugging, and that should do it. Also, I suppose while I'm waiting for any Q-colons, I might as well just take a look at these things. But you'll manage textures, width, height data. So we didn't do... there is one thing we didn't do yet, though, which is also the asset state thing. And so I don't know if that's that may be one that we have to deal with as well. Because once we add the texture up, we shouldn't really technically be using the we shouldn't be setting the asset to its final state until we actually do the op. So Dimitsuki, I've already said like 1,000 times I hate Vulkan, so there's never going to be a handmade Vulkan renderer, not from me anyway. Easy side. Do you need a safety write barrier before the current ticket increment inside Mutex unlock? No. So one of the things that's true pretty much across the board is where's my ticket Mutex at? So one thing that's true across the board is that atomics insert their own barrier. So basically, one of the nice things about a ticket mutex as well is that it actually naturally has its barriers on either side because these atomics serve as the barriers. So that's kind of nice, right? So you don't need them because of the atomics. If you didn't have those atomics, then you would have, right? But yeah. So at least as far as I know, there's no need to put any additional barriers, but that is a barrier. And yeah, the unlock. So this is, like I said, this is kind of an interesting aspect of the ticket mutex. Because you're issuing an atomic at the start and atomic at the end, they're naturally barriers. Other types of mutexes, which is I think what you were sort of assuming, where you said, oh, you missed the atomic at the end. Other sorts of mutexes don't have an atomic at the end, right? They may just do a regular set and they don't need to do it atomically, and then you would need a barrier. So yeah. Do you use an Srgb frame buffer and or premultiplied alpha? Yes, we use both of those things. We use both an Srgb frame buffer and premultiplied alpha. We use Srgb frame buffers, Srgb textures, and premultiplied alpha everywhere. Well, not everywhere. We do use non-premultiplied alpha for the secondary frame buffer. But everywhere else, we use premultiplied alpha. So all sprites are premultiplied alpha at the moment. But I'm not really sure. While I don't like that aspect of it, I'm not really sure that's a problem. Oh, you know what also I might do while we're here is the wiggle make currents thing here. Is it just init? Yeah, so this stuff, I want to get rid of this stuff. So there's no more thread OpenGLRC, any of that stuff. So this stuff should all, yeah, this should all go away. Goodbye. And all of this stuff should go away. So now we just have the one OpenGL-RC, and we don't ever have anyone else do anything with it, which is what we were trying to get to. One thing that's really nice about this is, as far as I can tell, that's 100% reproducible, which is great. So it means we should have a much easier time debugging it. You can imagine with something multi-threaded like that, we could have had a situation where like it was highly variable. $4.99. Can you explain about the secondary frame buffer not being premultiplied? What's the secondary frame buffer for? The secondary frame buffer is just to have a alpha composited upper layer. So I can actually show you what it's doing. It'll make a little more sense later on, but for right now you can sort of see, if I go up these stairs, do you see how it alpha blends a new floor in above me like that? In order to make that floor blend in seamlessly and not have the sprites disappear individually or be able to see through them or anything like that, that is what that's for. So it's that secondary frame buffer. And since that is rendered without, I didn't want to go have the renderer have to make it produce a pre-rendered alpha secondary frame buffer, because there's no reason to pre-multiply the alpha. Since it's never getting scaled, we don't actually need the alpha to be pre-multiplied. So it was just easier to leave it unpre-multiplied. But everything else is pre-multiplied because it produces more correct results. It might be pointless to do, but since you are using C++, have you used any ASM calls inside your code? You can't call ASM from C++ on Microsoft's compiler. You can in LLVM. So if we were using LLVM, we could have used ASM inline assembler, but you can't in Visual Studio. Why you can't in Visual Studio is beyond me. It's like, you know, it used to support it in the 32-bit, and I think still does in the 32-bit compiler, but then when they moved to 64-bit, like, I guess Microsoft had gotten so far away from ever knowing how a computer works anymore that they didn't think it was important to be able to put inline assembler into your code, which is stunning to me. I have no idea how you can even be a programmer and not think that inline assembler is important. If anything, they should have massively upgraded the inline assembler when they went to 64-bit and done stuff like made it easier to, you know, to never have to use like MASM or something, but they didn't do that. So, Baron is there a reason you're not using scope mutex guards that handle unlocking whenever the guard goes out of scope? Yeah, because I mean, what's the difference? It's just whether or not you put in curly braces, right? Like, so for example, begin ticket mutex. So you're going to put something around this, right? And so if I do it this way, that's what it looks like, and you can see it very clearly. If instead you use the scope mutex guard, then it looks like this. Right? So this is 5 lines of code. This is 4. So you've typed an extra line of code. This now can no longer, like if I wanted to do something with first texture op here, I couldn't, right? And hey, guess what? That's exactly what I wanted to do. So scoped mutex guards are garbage as far as I'm concerned. Like, I don't ever use them, I don't think. But they just don't map to the actual way that mutexes work at all, in my opinion. So I don't really ever use them. Other kinds of scope things I think make more sense, even in the case where they're not great. Like begin block, end block pairs, I do use scope stuff for, and you see me do like time functions. So I do sometimes have those. And temporary allocations I sometimes do. But mutexes just aren't that kind of a thing. That's just not the way mutexes work. Typically, you want to mutex a little tiny thing and then use the actual variables that you used in there, right? And so begin end is the right thing for mutexes, especially because it's not a mystery if you forgot to unlock the mutex. Your code will just hang immediately, right? So it's very unlikely that if you ever ran the code at all, you would know the bug immediately. It's not like memory where you might be worried about the fact that you could leak it, like you'd forget, so you want to make sure you do it when it goes out of scope or something. It's not like that. It's not a bug that you can really have particularly easily. So mutex guard, not so good. All right, I think that's all the cues, so I'm going to wrap it up. Oh, don't do that. All right. What was I going to say? Oh, yeah, so, and what I was going to say is, we still obviously have to debug that, so we're going to have to check it out tomorrow. It's kind of weird. I'm pretty surprised at the way... I guess I don't have a good guess. It looks like we ran out of something, right? Like, for example, if we mismatched our include... our mutexes there, which I guess we didn't because we only have 2 places where they happen. But maybe we ran out of stuff processing somewhere or orphaned something. But you can kind of see, right, like... we only have a few places where we do begin ticket mutex. We do a begin end there, and we do a begin end here. This is the definition of them, and here's the other one. So basically, we don't have any mismatched pairs, so we're probably not hanging up that way, but we've got something that we run out of, right? Something stops, and the way you can tell that is all those textures are loaded, right? But now we're not getting any new textures. Like, see if I turn the guy around and it tries to demand pages in, they never load. So I think we got a pretty good idea of what is happening here. We just got to figure out why we're draining out like that. And So, you know, if it's not the mutex, maybe it's, something with the free list or something where I don't know, we're not pulling from the right place, or we orphan something. So hopefully we'll be able to check it out. Tomorrow, hopefully we'll be able to debug that, and then we can cross that guy off the list too, because then we're down to just clan compatibility. And I think we can get that done before I got to go on vacation, in quotes. All right, so anyway, that's about it for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can play around with it yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot if you want to know when we're going to be live. You can subscribe to that and it'll tweet at you. And we've got a episode guide if you would like to follow along with past episodes like you did tonight. That's about it. I will see you guys tomorrow for the last stream of the week, 8 p.m. Pacific Daylight Time. Till then, have fun programming, everyone, and I'll see you guys on the internet. Take it easy.